Okay, let me try this integral again. So we're working with I of z equals the integral from 0 to 1 of e to the minus z t cubed dt. And we're taking z as complex and large, okay? So that means that z could be something like x e to the I phi, where x is real and large, and let's say positive, just to be clear. So in that case, I could write this as I of x equals integral from 0 up to 1, e to the minus x e to the I phi t cubed dt for x that's really large, okay? So now our rho function is going to be rho equals minus t cubed dI phi. That means that phi prime equals minus 3t squared e to the I phi. Rho prime prime is equal to minus 6t e to the I phi. And rho prime 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 is equal to minus 6 e to the I phi. So we finally get to a non-zero derivative on the saddle, right? So our saddle point here is going to be at t0 equals 0. And if we expand rho around that saddle point, we're going to get for t equals r e to the I theta minus r cubed e to the 3I theta divided by 6 times 6 e to the I phi. Okay, so the minus sign comes from that, which we can write as just r cubed, right? We can cancel these out and use Euler's formula, and we get r cubed minus cosine phi plus 3 theta plus I sine phi plus 3 theta. Okay, so now this is where we need to identify our directions of steepest descent. Okay, sine of phi plus 3 theta is equal to 0 because we want a constant imaginary part there that's equal to 0. That implies that phi plus 3 theta is equal to n pi. Okay, so it turns out for this problem we only need to choose one of these. So if we choose n equals 0, then we have that theta is equal to minus phi over 3. Okay, and that's consistent with where we need cosine of phi plus 3 theta equal to minus 1. That's going to be where phi plus 3 theta is equal to n pi for any n even. So we can take it to be n equals 0 again. Okay, so if we take n equals 0 here, okay, we're going to get theta equals minus phi over 3. Okay, but we could also write this, and this is what we're going to do, as minus e to the I phi t cubed. The imaginary value of that is equal to 0. And also we need that the real part of this, e to the I phi t cubed, is going to be less than 0 in order for it to be a descent. Okay, so we need steepest descent. We need the real part to go negative there. And so along the curve. So that means that taking these together, what we can do is we can parameterize our curve as e to the I phi t cubed is equal to tau, where tau is goes from 0 to infinity. So that'll be the curve that we integrate along, okay, for our contour emanating from the saddle point. Now, note here, if I draw this, right, here's our original contour that goes from 0 to 1. Here's real part of t, imaginary part of t. Okay. Now we're going to have some contour that emanates out from here, C1, and it goes all the way out to infinity. We need some contour that comes back and joins back here. Okay. So that occurs at t equals 1. And it turns out that for a method of steepest descent, in general, what you want to do again is you want to take that contour to be a steepest descent contour. Okay. So right at t equals 1, okay, or around it, you want this to be equal to just a constant value, which would be e minus e to the I phi, right, where t equals 1 in that case, or just minus sine phi in that case. So therefore, we have that e to the I phi t cubed is equal to e to the I phi plus just some real perturbation, which we can take. We need to join back from 0 to infinity. So that's going to be a curve that looks sort of like this, okay? And that's going to be our C2 there, okay? So there's this parameterization of a curve, and then there's also this one, and that is our contours now, okay? C1 is going to be e to the I phi t cubed equals tau, where tau goes from 0 to infinity. And in fact, in this case, t equals tau to the 1/3 e to the minus I phi over 3. That is going to map a change of variables. And so dt equals 1/3 tau to the minus 2/3 e to the minus I phi over 3. Okay. Our second contour is going to be e to the I phi t cubed equals e to the I phi plus eta, where eta now lives from 0 to infinity. And I can write t equals 1 plus eta e to the minus I phi to the 1/3, or for differentials, I get dt equals 1/3 e to the minus I phi divided by 1 plus eta e to the minus I phi to the 2/3 pound. Okay. So that's going to allow us to say, well, around here, there's no singularities, right? So our original integral, c minus the integral along C2 minus the integral along C1, right? Because the arrows are pointing the opposite direction, should equal 0. And so that means that the integral along C should equal the integral along C1 plus the integral along C2. Okay. All right. So that's great. So now we can just write our integral that we want to evaluate in terms of these two integrals here, okay, which may seem more complicated, okay, but fortunately they're doable integrals, okay. So we have that I now is equal to 1/3 e to the minus I phi over 3, integral from 0 to infinity e to the minus x tau, tau to the minus 2/3 d tau, minus 1/3 e to the minus I phi e to the minus z now, integral from 0 to infinity e to the minus x eta divided by 1 plus e to the minus I phi eta to the 2/3 d eta. Okay. All right. So now we can deal with these one by one. I'm going to call this one I1, and let's call this second one I2. So I1, we can actually evaluate using the gamma function. And remember, what's the gamma function? It's just that gamma of some a is equal to the integral from 0 to infinity of tau a to the minus 1 e to the minus tau e tau. So in fact, let's make it s just so we're not confounding variables here. Okay. So now what we can do is take our first integral and change variables. So then s is equal to x tau, or ds is equal to x d tau. So then I1 is going to become a third e to the minus I phi over 3, integral from 0 to infinity, e to the minus s now, s to the minus 2/3, x to the 2/3 over x d tau, okay? Or in other words, just gamma of a third over 3 z to the 1/3, right? Because remember, z is equal to x e to the I phi. Okay, great. The other thing is this is just equal to gamma of 4/3 over z to the 1/3. Okay, so great. So we got our first integral there. We can do the second integral using power series approximation. Okay, I2, and in particular, we're going to use like a binomial power series, and that allows us to write 1 plus e to the I phi. Make sure I did that right. Minus I phi eta to the minus 2/3 there, and making sure I don't mess up a minus sign there, is equal to this infinite sum now. Okay. Okay, so what is this coefficient here? The binomial coefficient minus 2/3 choose n. Turns out we can write it as gamma of a third, gamma of a third minus n, and then gamma of n plus 1. Okay. Great. So then I2 is equal to a third e to the minus z integral from 0 to infinity e to the minus x eta, sum from n equals 0 up to infinity, gamma of a third divided by gamma of n plus 1, gamma of a third minus n, e to the minus n plus 1 I phi now, eta to the n d eta. Okay. If you integrate term by term, you can get I2, which is e to the minus z over 3. Now the sum from n equals 0 up to infinity. So you see you have these exponentials times these monomial powers. So that's going to generate factorials, right, which will cancel this out. And you end up with gamma of 1/3, yeah, divided by gamma of 1/3 minus n, and then you get a z to the minus n plus 1, okay, from this, and then also the z that comes from e to the minus x, and multiplied by e to the I phi there. Okay. So finally, we can write I is asymptotically approximated by gamma of 4/3. This gets pulled all the way out in front. 1 over z to the 1/3 minus e to the minus z sum from n equals 0 up to infinity of z to the minus n plus 1 divided by gamma of a third minus n. Okay. All right. So steepest descent, right? For this finite domain, we used it to select our first integrals integration direction as well as our second integrals integration direction in terms of figuring out how to adjoin those contours back to the original line in that case. And we get the leading order behavior as well as all of these higher order terms, okay, from the steepest descent calculation, this expansion out to infinity. Okay, the main difference with what we've kind of done before is that we used sort of these explicit parameterizations of our direction of integration in the complex plane. And this makes it a little more transparent how the constraint on keeping the imaginary part of that function rho constant and keeping the real part of it negative so that you get a descent away from the saddle gives you this parameterization of these curves. Okay, so this is our solution in this case, and that is it for method of steepest descent and asymptotic integrals. We will pick up on ordinary differential equations on Wednesday. Okay, thanks.